Right, chemistry. Hey, we're going to go through and balance some equations. Now, these ones are written out in word form, so we're going to have to translate them from a sentence into the chemical compounds that are given and then balance the overall equation. So this is just a good skill to have. It takes lots of practice. It incorporates what we did last time with naming chemicals and writing their chemical formula. So it's a good place to start. It is challenging, so there are some practice problems I'm going to have you guys try and then submit on Canvas. But here's some examples, and so I'll go through them. Number one says when gallium metal is heated in oxygen gas, it melts and forms solid gallium 3 oxide. Okay, so first thing is to write the chemical species that are in the chemical equation. So gallium metal, it's just gallium, and if it doesn't say like that it's a liquid metal, a molten metal, or sometimes metals can be in gas form, but if it doesn't say, just assume that it's a solid metal. It's heated in oxygen gas. So oxygen gas is O2. Okay, and there are certain gases that actually will say atoms will bond to another atom of the same element and form what's called a diatomic gas. And it happens because the valence shells, okay, in those two atoms combine to form a molecule, and then they have a full set of valence or molecular orbitals, okay, that are very stable. So the diatomic gases, oops, I had them written over here, diatomic gases. And these might be a good thing to write down in your notes. Hydrogen, oxygen, nitrogen, chlorine, fluorine, bromine, iodine. Okay, those are usually group one. So hydrogen in group one, group seven, or oxygen or nitrogen are also common. But all of these will form gases that have two atoms of that element. So things to remember. Okay, gallium plus oxygen forms solid gallium 3 oxide. Now, if you're given an ionic compound with a metal and a nonmetal, it's probably best to write their ions and charges, okay, up above, and then translate it into a chemical compound. Now, gallium 3 oxide, I need 2 gallium ions and 3 oxide ions to balance their charges. Okay, so I brought that to +6 on the gallium and -6 on the oxygen, right? Multiplying by 2 and then 3. And that balances out to make a neutral ionic compound. Okay. And then after you've got all the chemicals written, then you need to go through and balance it. So we're going to save gallium solid for last since it's the simplest. We're going to start with oxygen. So I have 2 of them on the reactant side and 3 of them on the product side. So to balance it, I'm going to multiply that oxygen, O2, by 3 to get 6 atoms. Multiply this one by 2 to get 6 atoms of oxygen. Well, that gives me on the product side now 2 times 2 gallium, so 4. So I'm going to throw a 4 in front of that gallium. So that is a balanced chemical equation. Okay. Number 2. Liquid hexane burns in oxygen gas to form carbon dioxide gas and water vapor. Now, you're like, Mr. Ford, we haven't named something called hexane. So no, there's going to be some chemicals. We've just named mostly binary and simple ionic compounds and binary covalent compounds. So there are many common chemicals that we just haven't named, and a lot of chemicals will either get their names from other naming conventions, right, that we haven't talked about. Hexane is one of them. It comes from organic chemistry, and or they have common household names. And so you just get more familiar with these. You guys have Google at your fingertips. So you guys Google hexane, and it's going to say that is C6 because it's got hex, right? And then it's got 14 hydrogens. So if you Google hexane, it'll say C6H14 is its chemical formula. That's a liquid. Burns in oxygen gas. There's our diatomic gas again to form carbon dioxide. So carbon dioxide is CO2 and water vapor, H2O. Vapor is in gas form. So this type of reaction is called a combustion reaction. We're taking a fuel plus oxygen. Oops. and we're creating carbon dioxide and water. Okay, so if your two reactants are a fuel and oxygen and you get carbon dioxide and water as products, then you know you've got a combustion reaction. So this is one of the reaction types that's listed last in your POGL. Okay, so moving through here, we need to balance it. So when you balance a combustion reaction, you usually save the oxygen, the O2, for last. So I balance the carbons by multiplying this one by 6, right? That accounts for the 6 carbons here. I need to multiply the water by 7 to account for the 14 hydrogens there. And then I got to do some accounting. So I have 6 times 2, so I have 12 oxygens, and I have 7 times 1, I have 7 oxygens. So I have a total of 19 oxygens. Now, this one's a little weird. You're like, how do I get 19 oxygens on this side? So typically a chemist would do this. They would multiply this by, let's see, oxygen with a 2. I could multiply like 9.5, okay, by 2, and 9.5 times 2 is equivalent to 19. Okay, most chemists, right, would not write it as a decimal. They'd actually write it as an improper fraction. 9.5 is 19 halves. So this is probably the preferred way to write it. You may have learned in physical science or your 8th grade science class or earlier that you're not supposed to have like fractions or decimals in your coefficients, right? Those black numbers are called coefficients. But they're actually okay. Fractional coefficients are fine, especially if it has a half. This shows up a lot in combustion reactions. But if it bugs you, if you're like, well, my teacher, Mr. Ford, you told me in physical science that I'm not supposed to have, like, I'm only supposed to have whole numbers. What you can do is you can go back and double all the coefficients. So I like it this way with fractions, and most chemists would. But if it bugs you to have fractions and you're thinking, well, that should be a 9.5, but if I double that, that's 19. Well, then you need to go back and double everything else, including the guy in front. So that would be 2 hexanes plus 19 oxygens make 12 carbon dioxides and 14 water molecules. And if you balance it all up, I think you should have the same number of carbons, hydrogens, and oxygens on both sides. Okay, so fractions are okay. Improper fractions are best. And then, but you can double everything, right? And get rid of those fractions. So that's this one. Number 3. When solutions of calcium chloride and sodium phosphate are mixed. So calcium chloride, Ca2 plus, Cl minus. If you guys don't know these, you have your ion sheet, so you just refer to that ion sheet. Okay. So calcium chloride would take 2 chlorines, and since it's in solution, all right, AQ for aqueous, dissolved in water, plus sodium phosphate. So sodium is Na plus, phosphate, you look it up, PO4 3 minus. So it takes 3 sodiums and 1 phosphate. Okay, so there's my 2 chemicals, 2 reactants. It says when they mix, solid calcium phosphate forms. So this is a precipitation reaction. You're forming a solid, calcium phosphate. So calcium and phosphate. I think I need 3 calciums and 2 phosphates. So that balances the charge. This is a solid. Plus, you have leftover sodium chloride, and it says it remains in solution. Sodium chloride is table salt, NaCl, a +1 and a -1, and it's dissolved in solution. Okay? So, now I go back and I balance it. Let's balance the phosphates first. So I have 2 of them here, but only 1 phosphate. You can balance that whole ion by doubling sodium phosphate. That then forms 2 times 3, so 6 sodiums. So I need 6 sodium chlorides. Well, the sodiums are balanced, but the chlorines, I have 6 of them here. So to get 6 of them, On this side, I'm going to multiply by 3. And then I double check my calciums. 3 calciums on both sides looks good. So that is the precipitation. And if you're wondering, this is the precipitate. Okay, and that we know that that's the solid. That's the cloudy stuff we'd see in solution when those two reactants combine. Okay, that's also called, and just because we're talking about it in class, that's called a double replacement reaction or a precipitation reaction, and they usually are in the form AB plus CD goes to AD plus BC. So you can see A and B were partnered up, but now A and B are split apart. C and D were partnered up, but now C and D are split up. Okay, so they switch partners, or they swap partners, and that's typical of a precipitation reaction. Okay. Number 4, liquid disilicon hexachloride. So disilicon hexachloride, liquid, reacts with water. I'm going to assume liquid because it doesn't say water vapor or anything, to form solid silicon dioxide. Silicon dioxide. And again, I'm not balancing any of those charges. Silicon, oxygen, and chlorine are all nonmetals. So these are all covalent compounds. Silicon dioxide, and it says solid. Hydrochloric acid. Oops, and I put a typo in there. That should say hydrochloric acid and hydrogen gas. So hydrochloric acid is HCl, using our acid naming rules, right? Hydro is a binary. So hydrochloric acid, we list it as an aqueous. That means dissolved in water. And hydrogen gas. And you're like, okay, got to remember H2. That's on my list of diatomic gases. Okay. So hydrogen gas is H2. All right. That's a pretty nasty equation. I think we leave hydrogen for last. So we have to balance out the silicons first. So let's try this. 2 SiO2s. Okay, let's check the chlorines. Chlorines, I have 6 of them here, but I have only 1 of them here, so I'm going to put a 6. And then hydrogens. Okay. No, wait, we haven't balanced oxygens yet. Let's balance oxygens next. I have 2 times 2, which is 4. So I better get 4 oxygens. Okay. And then hydrogens, I got to add up. I have 6 of them here. On this side, oh, actually on the left side, I have 8 of them. And let's just double check. I have 6 of them, plus I have 2 of them right there. So I think if you add up your hydrogens, you've got 8 on both sides. So it is balanced with that 2 and 6 and 4. Okay, and I've been glossing over, I think, maybe on some of them. If they don't have a coefficient, there is a hidden 1. Those ones you don't need to write, but I'm just showing them. They are always there. If there's no coefficient, it just means there's 1 of that chemical. Okay. And then the last problem I picked, oops, has to do with, it's kind of a problem that ties in some atmospheric chemistry. So it says the loss of atmospheric ozone. So ozone is a chemical that's in the atmosphere. It's got the chemical formula O3. Okay, it has led to an ozone hole over Antarctica. The loss occurs in part through 3 consecutive steps. So in step 1, it says chlorine atoms react with ozone to form chlorine monoxide and molecular oxygen. So we can write and balance this one. Chlorine atoms, they don't tell us. This all happened in the atmosphere, so it must be gas, right? And this is weird because usually chlorine is on our diatomic list, right? There's chlorine, but they specifically said it's a chlorine atom. So this is probably happening way up high in the atmosphere where we've got some weird chemistry going on in play because there's so much ionization happening due to static electricity and um, radiation from the sun. So we get these what are called like radicals. So chlorine, even though it likes to be Cl2, up in the atmosphere you might find Cl atoms. So they specifically said Cl, okay, react with ozone, O3, and they form chlorine monoxide. So chlorine monoxide would be ClO and molecular oxygen. Now, they do say molecular oxygen, meaning it's a molecule or a diatom. So it's two atoms hooked together. And I think that is balanced already. You have one chlorine and three oxygens on both sides. So that one is done. Okay, chlorine monoxide forms ClO, OCl. And they write it like that because the chemical structure of it with its covalent bonds probably looks something like that, where it's got some structure with chlorines on the ends and oxygen in the middle. So they write it differently so you can tell its structure. So chlorine monoxide, ClO, forms ClOOCl. Well, I think I need, oh, and these are in gas phase. I think the only difference is I need two ClOs, right, to balance it. And then that gives me two chlorines and two oxygens on both sides. Okay, next, it says the ClO-OCl absorbs sunlight and breaks into chlorine atoms and molecular oxygen. So ClO-OCl absorbs sunlight. Okay, say sunlight. And it breaks into chlorine atoms and molecular oxygen. This one, I think I just need to double. Let's see, I have two chlorines on the left, so I need two chlorines, and I have two oxygens on the right. So we're good there. And so these are the three reactions that are happening. And it says, now it gets confusing when they're in three steps. So I have 1, 2, 3 steps. And it's, they're all CLs and O's, and it's hard to tell what chemical is what. So a lot of times chemists will take their reactions and you can combine them and get what's called an overall reaction. So what I'm going to do is I'm going to look at everything on the left-hand side of the reaction, everything to the left of the arrow, okay, in each step, and I'm going to write those down. Okay, so I'm going to do this. This is a little overkill, but I'm going to go through it. So Cl, I'm going to drop the G. Everything's in gas phase, plus O3, plus 2 ClOs, that's from step 2, plus ClO-OCl makes, and then I'm going to take everything else that's on the right side or the product side, and I'm going to write that on the right hand side of the arrow. So ClO plus O2 plus ClO-OCl plus 2Cl plus O2. Okay, now that's everything from all three equations combined. And then what I can do is I can go cancel things. So if I have something that's the same on the left and the right, I can cancel it. So this and this, right? The ClO-OCl is a reactant and a product. So it cancels. This is just like canceling in algebra. You can remove things from both sides of the equation. I have one ClO and two of them here. So I'm going to cancel out just one of them. Okay, I can't cancel both of them, but I can cancel this one and I can get rid of one of these. So now I just have one ClO. So let me erase this. I'll just change it to a 1. Oops, wait for my pen to come back. Okay, and then I can do the same thing with chlorine. I'm going to get rid of the 2 and put a 1. and I'm going to cancel out the chlorine here. And so overall, let's see what we are doing. Oh, and I can combine. I have two O2s, okay, on the right-hand side, so I can rewrite that as two O2s plus 1 Cl. And I have on this side O3 plus ClO makes two O2s plus a Cl. Okay, so that is the overall reaction, and I think it's balanced. I have 4 oxygens on both sides, yep, and I have 1 chlorine on both sides. So what's happening overall is I'm depleting ozone, and I am forming oxygen. So I'm taking away ozone from the atmosphere, right? Which helps protect us from ultraviolet radiation, and I think, let's see what else. It's part of our atmospheric layer, right? It either protects us or helps keep radiation in. But by taking it away and depleting it, we're forming more oxygen, O2, and we're losing out on the ozone. So, and that was a bigger deal when I was in grade school. I remember current events always we talked about the hole in the ozone layer. It's less and less of a problem because we're putting less chlorine. Okay, we're putting less chlorine into the atmosphere to deplete, and other refrigerants, right? A lot of refrigerants have chlorine in them, and we're putting less of those into the atmosphere, so we're having less problems with this ozone hole. Okay, so hopefully, and this was a big problem, that overall reaction, probably not something we're going to ask you guys to do, but I thought it was just interesting. So more is, can you guys write out the chemicals and balance? So I'm going to give you some to try, and that'll be your asynchronous activity for the week. So good luck.